Welcome back to the deep dive. So if you're looking at building something complex, something really mission critical, especially across, what, 6 platforms?
Yeah, 6. Android, iOS, Windows, macOS, Linux, and web.
Right. You really need a solid plan, a blueprint. Guesswork just won't cut it. Today, we're cracking open the client side, the Flutter side of an app just like that. We're talking stability, scaling up, and crucially, that responsiveness you need for, well, real-time features.
Exactly. Our goal here is to give you that blueprint. If you've ever felt, buried trying to manage a big Flutter project, or maybe you've hit a wall trying to implement tricky things like really fast local file sharing, this should be super valuable. We're getting into the architecture, clean architecture, feature first, and the actual tools, the dependencies that make it all work.
Okay, first things first, 6 platforms. That's a huge target list. Why Flutter? Why was that the choice here instead of, other options?
Well, it really boiling down to one main thing: consistency. Shipping to 6 different OAs from just one code base. That's a massive time saver. Huge advantage for getting to market quickly. And the code reuse. It cuts down maintenance like crazy. Fix a UI bug once, it's fixed everywhere.
But lots of frameworks promise that one code base thing. What was the real technical clincher for Flutter? It wasn't just Dart, was it? It's more about how it renders, making sure it looks exactly the same.
That's it. You hit it. The Skia engine. That's the core magic, really. See, unlike frameworks that use the built-in widgets from the OEM widgets, Flutter draws everything itself, every pixel.
Yeah.
It uses Skia, which is basically a 2D graphics library that gets bundled right with your app.
Huh. So if Windows pushes an update that changes how buttons look, or iOS tweaks its navigation, the Flutter app just ignores it. Stays the same.
Precisely. That guarantees real visual consistency and behavioral consistency, too. You get pixel-perfect control. No platform drift messing things up. Plus, Flutter's reactive nature works really well with the state management we chose, BLoC, which we'll get into. It's great for real-time updates.
That level of control sounds amazing, especially if you have strong branding needs. But okay, let's be honest. What are the downsides? Where did Flutter cause some friction?
The main one, almost always, is app size, the final binary. Because you're bundling that Ski engine and the framework, yeah, the initial download is definitely bigger than a pure native app. It's a trade-off for consistency. The other challenge, and this is pretty relevant here, is getting deep into platform specifics. When you need things like very specific local network permissions or accessing certain device IDs, you often need to write platform channels.
So writing little bits of native code, Kotlin or Swift.
Exactly. To talk back and forth with the Dart code. It adds complexity, no doubt. More layers than if you just went fully native from the start.
Okay, Flutter's the tool. Now the structure. 6 platforms. Tricky features. You can't just wing it. Code-based chaos is, like, the enemy. You mentioned needing a governing principle, and you landed on 2 big ones: clean architecture and the feature-first pattern. Why go so strict?
For something this big, stability and scale were paramount. Clean architecture gives you that separation of concerns. It's like guardrails against bad habits. Think of it as layers, concentric rings. The core business rules are totally insulated from the UI or the database or the network. They stay pure.
Sounds good conceptually, but for someone listening who hasn't done clean architecture, what does that look like in practice, in the actual folders?
Okay, imagine building some complex machine, the domain layer. That's your core blueprint, the engine itself. All the fundamental business logic lives there. Your models like user or file, and importantly, abstract interfaces like contracts saying what data should look like but not how to get it. And the key, this domain layer, it never imports Flutter code, ever. It has no idea if it's talking to a REST API or a local file. It's totally independent.
Right, so the business logic is protected. It doesn't care about the tech stack around it. So where's the part that does care? The part that actually talks to the outside world?
That's the data layer, the outer ring, the implementation details. And the domain layer says, I need files. The data layer figures out how. It has the concrete implementations of those interfaces from the domain layer. It uses specific packages like DO for hitting the Node.js API or talking to Backblaze B2 storage. All the external stuff lives here.
Okay, domain for rules, data for external connections. Where does the Flutter UI and state management hook in?
That's the logic layer, sometimes called a presentation or application layer. It's the bridge. This is where our BLoC classes live. Take input from the UI, maybe tell the domain layer to do something, then use the data layer to fetch or send information. And the payoff is huge. If we decide later, hey, let's ditch DO and use a different HTTP client or change cloud providers, you only touch the data layer, the domain and logic layers. Untouched, saves massive headaches down the road.
That makes total sense for keeping things separate vertically. What about horizontally? That's where feature first comes in, separating by user journey.
Exactly. Instead of one giant models folder, one giant views folder. You slice the app vertically by feature. You'll have folders like authentication, cloud, dashboard, profile. Each one is kind of a mini app inside the main app. It has its own BLCs, its own models, its own UI screens. The big win, it minimizes dependencies between features. Someone working on the dashboard isn't likely to break the profile screen by accident.
Yeah.
Makes it way easier to scale the team, test things, and onboard new devs.
All right, let's zoom into that logic layer, state management. You chose BLoC business logic component, given the real-time needs, WebSockets, all that. Why BLoC specifically over, say, Provider or Riverpod?
Predictability. With WebSockets firing updates, local network stuff happening, you absolutely need to know why the state changed. BLoC gives you that. Its whole model is built on explicit streams of events going in and streams of states coming out.
Can you walk through that? An event goes in, a state comes out.
Yeah, so the user taps a button to share a file. That action is packaged up as an event like share file requested event. The BLoC listens for these events on the event stream. When it gets one, it performs the necessary logic, maybe talks to the domain layer. Then it emits a new state onto the state stream. The UI just listens to this state stream, so it might emit transfer in progress, send 50, or transfer error state message network failed. The UI just rebuilds based on the latest state it receives.
Oh, okay. So it's a very clear cause and effect. Input event, output state. Must make debugging way easier, especially with asynchronous stuff flying around.
Totally. It makes state changes deterministic. You can trace the exact sequence of events that led to a weird state. Super crucial for real-time apps. And another huge plus for BLoC, testability. Because BLoCs are just plain Dart classes, they don't depend on Flutter widgets at all. You can unit test them easily with tools like BlockTest and Mocktail. Make sure the logic is solid before you even involve the UI.
Okay, this structure, this predictability, it feels like it all leads up to handling the really complex stuff, like that local file sharing feature. This isn't just fetching some JSON data, it's moving potentially large files quickly between devices on the same network. How did that technical dance work?
Right, this is kind of the aha moment for the whole setup. It's clever because we use the cloud, but only for coordination, for signaling. The actual heavy lifting, the data transfer, that bypasses the cloud completely. It's a multi-step process, like a handshake. Step 1. As soon as you log in, the Flutter app opens a persistent WebSocket connection to our Node.js backend. That socket stays open. It's used for notifications, seeing who's online presence detection, and all the signaling messages.
Okay, so the server knows who's online. But if I want to send a file to you on the same Wi-Fi, how does my app know your local IP address? The server only knows my public one.
That's the twist. The Flutter client has to figure out its own local identity. It uses packages like Network Info Plus to find its own local IP address on the network and finds an available port. And then this is the really cool part. The Flutter application starts its own tiny HTTP server running right inside the client app itself.
Whoa, hang on. The client app is running a server just to receive files. That sounds potentially complicated with permissions and stuff, but technically really smart for speed.
It is specialized, yeah. But it's the key to that low latency. Once that mini server is up and running locally, the app sends its local IP and port number up to the Node.js server through that WebSocket connection. The server just stores this local address in a registry, basically. It maps your user ID to your current local IP and port. Now, the handshake itself. Let's say user A wants to send to user B. User A's app asks the Node.js server, hey, what's user B's local address? The server looks it up, sends it back to user A, and also sends a message down the WebSocket to user B saying, hey, user A wants to send you a file. The server is just the matchmaker here.
Got it. So the server connects them by sharing the local coordinates, and once user B accepts,
the server steps out completely. The cloud is out of the picture for the actual data. User A's Flutter app then makes a direct HTTP POC request, sending the file data straight to user B's local HTTP server IP and port. The file goes straight across the local network, peer-to-peer, essentially orchestrated by the server, super fast, limited only by the local Wi-Fi speed, not internet bottlenecks.
Wow. That flow, WebSockets for the setup, local HTTP for the data is really neat. Okay, let's quickly run through the key packages the toolkit needed to pull all this off.
Yeah, the dependencies really map back to those architectural layers we talked about. For the core architecture and state management, it's mainly Flutter BLoC and also Equatable. Equatable helps make sure BLoC only emits states when things actually change. Keeps things clean.
And for handling those connections, the WebSocket and the direct HTTP.
For the persistent connection to the backend, WebSocket channel is the go-to, simple and effective. For the regular API calls, and also for making that direct POSD request for the file transfer, we use Dio. It's a powerful HTTP client. We often pair Dio with Retrofit, which can auto-generate a lot of the boilerplate client code from annotations. Speeds things up. But the really crucial ones for that local transfer magic were the device-specific packages. Network Info+ to get that local IP address, and Device Info+ to get other unique device details sometimes needed for registration or identification. Couldn't do the local server trick without them.
Makes sense. And rounding it out, data storage and navigation.
For local storage, we needed speed.
Mm.
Hive and Flutter give you super fast key value storage, great for caching. And for anything sensitive, like OGG tokens, we use Flutter Secure Storage. Uses the platform's secure storage mechanisms. Then tying it all together, navigating between all those feature-first modules, GoRouter worked really well. It's declarative, URL-based, pretty easy to manage. #tagoutdirect.
This has been quite the journey, from the high-level decision of why Flutter for 6 platforms, down through clean architecture's layers, and landing on that really clever local transfer handshake.
Yeah, and I think the main thing for you listening is just remembering that architecture is truly an investment. Taking the time up front to define patterns like clean architecture, like feature first. It feels slower maybe, but it saves you from drowning in technical debt later on, especially when you get into complex territory, like, well, running a server inside your client app.
Right, we established that happened here specifically to make local transfers faster by skipping the cloud.
So thinking about that capability, a local server running inside the app, it really opens up some interesting possibilities, doesn't it?
Yeah.
What else could you do with that? Think about apps that need to work flawlessly even if the internet connection is flaky or gone completely, or features that could just run entirely on the fast local network. What other functionalities could shift away from relying on the cloud, moving closer to the user onto the device itself? That's something to really chew on for your next big project.